Okay, so in the MATLAB, you can do some work and save your work, like saying save. If you say save on MATLAB, actually, it saves all the workspace to a file. We have to specify the number and name of the file. And it can be a mat file, which is a binary file, or it can be a dat file, which is a data file, so that you can see the data inside it. The M files are files you can create or people can create in addition to the basic functions of MATLAB. So you can write functions and run them on MATLAB, and they get added up to MATLAB. There are lots of predefined functions, by the way. For example, taking square root, size of a matrix, square root of sign, eigenvalues, eigenvectors, exponentiation, logarithm. This log is for ln, and log 10 is for logarithm to base 10, by the way. You can use the help function to get help from MATLAB. If you want to say help, it gives general help, but if you say help and the name of the function, it gives you the help about that function. You can use trigonometry functions. You can use statistical functions like mean, sums, products, variance, standard deviation, etc. Now the commands, instead of writing commands in the screen, you can write the commands on an editor and save them, and then if you run the M file, you will run those commands sequentially. That's what the MATLAB does. And also you can use this this two dots on top of each other, this quant thing, for example, results in, let's say that there is an example here, x equals 1 by 2 to 13. So it results in a vector like 1, 3, 5, 7 to 13. So it jumps 2 by 2 in order to reach to 13. Minus 3 to do results in a vector from starting from minus 3 to 2, for example. If you want to create a vector linearly spacing, let's say something between 0 to 8, with 6 data points, you say linspace 0 to 8.6, and you get this, for example. And you can also have logarithmically spaced by log space. That's another thing. So to generate the matrix, for example, this matrix, you just type the matrix with semicolons, as I have said, so that you generate the. There are special matrices like zeros of size m and n, ones of size m and n, and I is a matrix of an identity. I of 3 gives you a 3 by 3 matrix, for example. If you take the transpose, A transpose is given by this well, what is this thing? Let's say comma on top of it, gives you the transpose of this matrix. So if you want to select one element, let's say x of 4, if x is this vector, x of 4 gives you the fourth element. And if you say x of 4 equals 12, in that case, the fourth element of x is changed to 12, for example. And also, for example, A23, if you say A23, it displays you minus 2, for example. If you say A23 equals 12, then you replace this minus 2 with a 12. Everything else remains the same. The colon, this two double dots on top of each other, colon is an important operator. For example, x colon in parentheses gives you all the elements of the vector. If x m to n refers to elements m to n of vector x. A colon n, for example, refers to all the elements in the of the rows in the column n of the matrix. So all the elements in of all the rows in column n. A n colon refers to all columns in the row n. I guess I need to give you an example about this. This is a little bit tricky. So let me, I have to stop this and go to MATLAB or Octave. For example, A is this matrix, right? 1, 2, 3, 4. For example, you see it, right? A of So, for example, A of all the elements in the first, all the rows in the first column is 1 and 3. All the rows in the second column, for example, is 2 and 4. For example, 2 and 4. All the columns in the first row is 1 and 2, and all the columns in the second row is 3 and 4, for example. For example, B is this vector. If I say B, this would be B of 1 to 3. For example, let me make it a little bit larger. C equals, let's say, random numbers of 1 to 10, let's say. It gives you 10 random numbers starting from 0 to 1. I can say C equals C transpose, for example. Okay, so there are 10 random numbers. For example, C of 3 to 7 this is a small C. So it gives me C from starting from 3 to the 7th element part only. Okay, this is what this thing says. And also I can change, for example, C of 5. For example, I can say that it is 1. If I say that now, the 5th element of C has changed to 1, but all the others remain random numbers. Okay. Let's go back to our presentation. Okay, this was, I think, where we were. So you can change the dimensions of matrices or vectors by assigning new elements. You can delete the elements. For example, if you say x of 3 is equal to 2 brackets, that means an empty set, an empty number. This means delete the third element of x, for example. In this case, x becomes 1, 3, 5 is deleted, 7, 9, 11, for example. And you can partition a matrix. For example, you can say the 2 to 3, what is this? 2 to 3 columns. Which ones will that be? 1, 2, 3, 3, 4. What is this? What is this? Just a second. This is the rows of second and third columns, second to third columns. Okay, what this does is, sorry, all the rows of second to third columns are deleted. So this part is deleted. Okay, so what you get is 135 and 706. This part now is gone. This is what you have as A. And let me quickly talk about plotting. If you want to do plots, you just define two variables and then two, let's say, vectors, x and y, and find, you just say plot y with respect to x, you say plot x, y. So let me show that on Octave. For example, t is, let's say, t is time from 0 to 0.1 to, let's say, 10. T is a vector, linearly spaced vector starting from 0 to 10 with the intervals of 0.1. So if it has 100 elements, let's say y is t plus sine of t, something like this. It doesn't matter really. If I put a semicolon at the end of it, it doesn't show me y, but I can now plot t versus with respect to y. Do you see the plot? Probably you don't. Oh, you do? Okay, so this is the plot. For example, I can say z is let's say it is another function. Is, let's say, minus t plus, let's say, cosine of t. I don't know. I just made it up. Now we have two different y and z. I can plot them together. Why don't we have it? Okay, plot t. For example, I can combine y and z as a single vector and plot it. For example, as you see, I now get two plots, right? I can do normal plots, I can do logarithmic plots, etc. I can extend this plot. Where is that? Make it larger, I guess. I can put a grid on the plot, like grid. You see, now you see grids on grid lines. What else? This plot can be logarithmic. It's a bit strange to do that, but let me do it. For example, log of t versus y. Well, it didn't work because there are probably zeros somewhere. Yes, question? Go ahead, please.
Jim, the same commands hold up for MATLAB as well?
Yes, they do. They are exactly the same.
Exactly
I said
the same.
the MATLAB and Octave are 99% equivalent, okay? The only thing the Octave doesn't have is Simulink. Simulink is a graphical software. MATLAB has it. Octave doesn't have it. Okay, but we are not going to use Simulink in this course, so it doesn't matter really. There are very, very few functions which MATLAB has and Octave doesn't. So, so I can just go ahead with MATLAB with Octave today anyway. Okay, the log function didn't work because I think there was a zero somewhere. Well, one of them worked actually. You can use semi-log plots like for example, semi-log x of ty, you can say. Still, there is an error, I think, because there is a again a zero somewhere. But this plot is logarithmic in the x-axis, for example, and so on. These are the plots. So let me go to our presentation again. So I can put multiple plots, like two things together plotted with respect to y. I can plot f plot function, for example, plots functions directly from minus this function, for example. By the way, it is enormously big. You cannot imagine how big it is, the MATLAB, how big it has become. You can put logarithmic plot, bar plots, histograms, etc. Subplots are, you can have two plots in the same chart, in the same picture. You can do matrix operations. That is the main starting point. You can have dot product. Multiplication of matrices is very simple. It's you just say A times B, for example. If A is a matrix, B is a matrix, is A times B. By the way, for example, A dot time A dot, and then the times operator B means element by element multiplication. That's another multiplication you can do. It's not the real multiplication. You can find the inverse of a matrix by inverse of A. You can find the square of a matrix, that is A times A. For example, A dot exponent 2 means element by element square of matrix A. It is not the same as A times A, obviously. Determinant is the determinant of A. You can find the eigenvalues of A. You can solve linear equations. For example, with x equals A inverse of A times B, or you can use this matrix division, like A, B divided by A kind of operation, in which you have the solution. In this case, this is a better way of solving the mathematical problem. There are special matrices like these, identity matrix, diagonal matrices. Diagonal gives you a diagonal matrix. The elements on the diagonal are zero. Anyway, the matrices is not our specialty in this course. We will be more interested in the transfer functions and so on. So let me go on to those things. So I'll to system response with MATLAB. I have uploaded this thing. This is from Ogata's book, as I have said. If you want to represent transfer functions in MATLAB, you just write the numerator like a vector and the denominator as another vector, okay? And then, well, you can do the partial fraction expansion, but I'm not interested in the partial fraction expansion really. What we are really interested is to find the transfer function of. It would be good if you could read these notes by yourself, residues and so on, but I'll skip those. Okay, now you can define a system data structure like G as transfer function of the numerator and denominator. For example, this thing with a numerator and denominator of this size will give you, if this is the input U, if this is the output Y, the transfer function will be TF of num and den, as you see here. That defines a mathematical data structure. Let me try to do this in MATLAB. And after that, for example, you can find the step response of this system saying step. Let's do it now in Octave. Now, okay. So numerator is 2, 1, let's say. Denominator is 1, 3, 3, 1, let's say. I just made it up. Now, the transfer function command, in the beginning, it won't work. Let's see. Let's say G is equal to TF of num and den. We'll say TF is in control toolbox. You have to say this PKG load control. So PKG load control. And once you load it, it will be the load control package is loaded now. Now you can, if you do it, you see the transfer function is defined now. You can say step response of G. And you see the step response, right? And the step response is up to time 6, it seems. We can increase this by saying step of G up to, let's say, 20. Now the response is up to 20, as you see. Step response can be found. Now we can combine transfer functions. How do I do that? Okay, so I have a G. G is a transfer function like this. Let's define another thing. Let's say G2 is transfer function of 1 is the numerator, let's say, and 2 and 1 is the denominator. So it's 1 over 2s plus 1. Now, G, we have two transfer functions, G and G2. For example, I can say G, well, how can I say it? G and G2. So let's say G1 is G times G2. Now I have multiplied two transfer functions. I can say the same thing by G1 equals, G1 equals series of G2. You get the same result as before, as you see. I can just directly multiply them. And let's say we have an H. Let's say H is the transfer function of 1, 1, let's say. So 1 over s plus 1. And let's say that H is in the feedback path, so that I can say T is equal to feedback of G1 and H, for example. So this gives me a feedback transfer function. I can, for example, say the step response of H can be found. This is short, so let's make it a little bit longer. Let's say up to 10. So we see that we have a response reaching to 10 seconds. This is the step response of the closed loop system, for example. Okay, let's stop this and go back to our presentation or our system response. So we find the step response by saying y steps. If you can specify the time, if you like, or you can find the time. You can also find the step response by just saying num and denominator. For example, you can go through these examples if you like. Step response is found here. Another step response, unit step response is found here. Another example with a step response is here. Actually, you have two step responses plot on top of each other. Okay. You can also find the impulse response and so on, but I didn't include that in the presentation. Okay, let me go with this block thing. Okay, we can represent block diagrams in MATLAB, as I have said. Series blocks, for example, can be multiplied with each other by saying series, or you can just multiply, use the multiply operator. That made it a little bit easier. For example, the series gives you the following. Skip this transfer function, the state space thing, we didn't learn that. You can add parallel blocks, for example, using the parallel command like this. Parallel sys1 and sys2 gives you the sys. Okay, this is the parallel. And there is the feedback command, which is feed-forward transfer function, and the feedback transfer function can be combined to get the feedback transfer function, as you see. Okay. And once you get that transfer function, the closed loop transfer function of the feedback system, you can find its poles and so on to find how it is operating. For example, you can say, let me go back to, where is that? Okay, so we have the closed loop transfer function, T, for example. T is the closed loop transfer function obtained from the feedback of, where is that? G1 and H, let's say. Let's make it, let's say T is feedback of G and H, let's say. Okay. So T is obtained combining G and H. Poles of T. I'm not wrong. Poles doesn't work. I think it should be pole of T. Yeah, gives you the roots of the denominator of the transfer function, the closed loop transfer function. As we see, they are all negative, which means that the response of this system is going to be, this is step, I'm sorry, I should have said step T. I said of H, which gave me the step response of a first order system. Yes, yes, I'm listening.
Hojam, can you please explain again how you found the poles of the denominator in order to understand if the values that we obtain are in the real or imaginary parts of the coordinate system of?
Now, I said, let's say G is the feed forward. In the feed forward the transfer function, you have G. This is G, right? And our H is the feedback transfer function. Let's say it is 1 over S plus 1 for some reason. Now, I combine them by feedback. I say T is the feedback connection of G and H, right? So this is the closed loop transfer function. Now it has a numerator and it has a denominator. If I say pole of T gives me the roots of the denominator, as you see, which is this s to the 4s cubed, 6s squared, 6s plus 2. And as you see, they are all negative, so the closed loop system is stable, and we can see that by plotting the step response, which is something like this, for example. It is stable. I can also do the following. Instead of saying T, I can say NT and let's say DT, numerator and denominator. Sorry, it didn't work. Okay. So, anyway, I can just say pole of T. These are the roots of, for example, roots, if I say, of this polynomial, which is 1, 4, 6, 6, 2, is the same as the poles of T, as you see. Okay, these two things are the same. Okay. So I can do the feedback connection. I can, for example, use a PID controller. Let's say I can use a PI controller. So this is a PI kind of controller. Let's say G1 is the PI times G. Oops, sorry. G. So this is a system in the feed forward. And let's say T is feedback of G1 and 1. Let's say that in the H model would be 1. So the pole, let's say, of T, well, they are still negative, but I'm not sure this will be very good response. Let's look at the response step of T. Is going to be, actually it's quite good, yeah. This will be the step response of a PI system with a PI controller, for example. Do you have any questions? Okay. I guess you don't have questions. Let's take a break for now for some time. Yes, I'm listening.
Hocam, I'm so sorry. I seem to be the only person asking you the questions,
It's all
and
right.
I really do apologize if I kind of seem to be annoying you.
No, you are not. Actually,
All
I
right.
want people to ask questions. Yes.
Hocam, the thing is, I mean, with these lectures and everything, Hocam, and especially with the homeworks, where we actually have to use the MATLAB software,
Hmm.
Hocam, it would be really, really effective for us to have for example, if there's a TA or something, or like extra office hours where we can discuss our ambiguities, which if we discuss in normal lecture hours, would waste your time and the other people's time asking those questions. I mean,
Hmm.
that's all I'm saying. If we had those extra lecture
Okay.
office hours or something.
Okay. Your TA is Matthew Aras. I will talk to him. He can possibly arrange an office hour with you about MATLAB and so on, if you want. I can arrange that. It's a little bit late in the semester, but we can do that if you like. We should have done it maybe earlier. We can do that. By the way, let me